Hello and welcome to part 5 in a series of recorded walkthroughs of the United Kingdom Terminology Centre's Data Migration and Analytics Workbench. This is a proof of principle application written in Microsoft Access, demonstrating some of the properties and the possible advanced uses of our data migration mapping products and of the terminologies and classifications that they link. The application is divided into 4 main areas of functionality: the text-based console, which is displaying now, and 3 graphical tools to browse the cross maps, construct query specifications, and perform EPR data analytics. This walkthrough provides an overview of part of the 4th of these areas, the EPR data analytics tool, which can be opened by pressing the button at the bottom left of the console, although I have one open already. Part 4 of the walkthrough series explained how external real patient data can be imported into the tool, checked for errors, data repairs can be declared and applied, and the repaired data can be cross-mapped to a number of other terminologies and classifications. And the tool displaying now has around 182,000 patients' records loaded, and the data has been repaired and cross-mapped. And we can now move on to the analytics functions of report, trends, induce, and graphing, beginning with the reporting function. This generates one of the simplest and crudest outputs of the workbench, a single text file listing information such as the age-sex distribution of the patients that have been loaded, and some information about the coded data, including which chapters of SNOMED or other classifications they appear in, and lists of the top 10 diagnostic categories for each age-sex cohort. When it does finish, some 4 or 5 minutes later, you get a report like this and a dialogue. The report that comes out tells you the outline or the contents of the full report, which is saved to a text file on the hard disk and also already open, as it says here, in Notepad. So if I click that, I should find at the bottom of the screen the full report appears here. So it's not pretty to look at, but it contains a lot of interesting information, beginning with a basic demographic analysis that has nothing to do with the coded part of the data, and then moving on to information about the outcomes of the consultations, the age, sex profile of the population, and then down to some coding analysis, beginning with a breakdown of which major chapters of SNOMED content the coded episodes are found in, and not surprisingly, given the purpose for which the coding in this case has happened, most of the codes are either a disorder or a finding, with a small number of procedures and situations, and then very small numbers of codes in each of the following chapters of SNOMED. These very low counts in themselves are very strongly suggestive that these chapters probably are inappropriate to use under any circumstance. And there are further analyses which can make interesting reading in the full list. So now we've done a basic import of the data, a check and repair of the data, cross-mapped it, and produced an outline summary report. Now we can go on to the next basic analytics option, which is the trends module. Again, the output of this report, which takes a little while to compute, is primarily text. The goal of the trends report, which is displaying now, is to analyze the electronic patient repository to find individual codes which have exhibited either a significant increase or a decrease in their usage. To do this, all the episodes of care encountered in the entire repository are divided into 2 portions. The first period in this particular case is the first 12 months out of the 39 months of data that was imported, and the second period is the last 12 months of that 39-month period. The little report at the top tells us that overall in the entire data set there's a little over 400,000 episodes of care, of which 120,000 fall in the first reporting period and 130,000 in the second. And it notes at this point that there is a 10% increase in the overall coding volume that occurred in the second period by comparison with the first. The body of the report is in two halves, a listing of the codes exhibiting the largest increase in frequency of use, and this is followed by a similar list showing the codes with the largest decrease in code usage. So, for example, the three codes at the top of the biggest rises chart are the code for generally unwell, abdominal pain, and chest pain. The number of episodes coded with generally unwell has almost tripled between the first and the second reporting period. The increase for abdominal pain is rather more modest, roughly 50% more, and so on down the table. The absolute value here is the absolute increase between the number recorded in the first period and the number in the second period. The relative increase is a measure of how much of the overall increase exhibited across all codes in case mix, i.e. this 11,000 increase here, is accounted for by this increase. So in other words, we're saying that out of the 11,000 extra cases that were observed in the second reporting period, it is possible that 20% of it is accounted for entirely by the increase in the use of the code generally unwell. However, we can't tell whether or not the increase in the usage of one code was at the expense of a corresponding decrease in the use of a very similar code. If that was so, then in fact the underlying incidence of, for example, chest pain may not in reality have changed at all. All that's changed is the code that the clinicians are using to record it. In order to compensate for these kinds of effects, where the coding of data shifts between different coding behaviors, whilst the underlying incidence of disease stays the same, we need to adopt a different approach for analyzing the data. And this is the function of the INDUCE button. A detailed exposition of exactly how the INDUCE function works and what it's aiming to do is outside the scope of this particular walkthrough. As the dialog says, the analysis takes a fairly long time to run. Between 15 minutes and half an hour is not unusual for a dataset of the currently loaded size. I'll set it running and we'll come and have a look at the result at the end. So some 18 minutes later we're back with a lot of fairly incomprehensible text and a rather Delphic dialog box saying that it's finished the induction process. Exactly what has been induced is visible in the query section, and the value of it is demonstratable only really using the graphs portion of the data analytics screen. First, let's take a look at exactly what has been induced. So we'll flip back to the query panel, make the font a little bigger, and move over to the editing pane, where we'll see this newly induced cluster. So the INDUCE process results in the generation of exactly one new cluster. And the new cluster has 121 clauses, which between them will subsume almost all of the coded content within the patient record dataset that was analyzed. And we can demonstrate this within the query tool by running the test query function. We'll ask it to retrieve the codes. So some 4 or 5 minutes later, the tool comes back with the result displaying in the right-hand pane. And this tells us that the 112 clauses that were induced in the cluster, between them subsume 97.5% of the entire body of coded EPR content, the 400,000 episodes of care, expressed using around 12,000 different SNOMED codes, of which around 11,700 of those individual codes fall between at least one of the 112 clauses in the induced cluster. So essentially what has happened is a classification of the entire EPR content has been induced as a series of 112 mostly discrete but potentially overlapping categories, And the particular choice of categories that has been made is tuned so that they account for broadly equal proportions of the entire record. So as we would expect in an ED department, there are certain categories, like degenerative disorder, which do not account for a significant volume of the patient case mix load of an emergency department. There is a little bit, but the number of patients with arthritic and other degenerative conditions will be relatively small, and therefore in order to aggregate a large enough group of patients, the abstraction algorithm has pushed quite a long way up the SNOMED taxonomy to a relatively abstract concept. In the same way, we'll find that other disorders so of the immune system and the lymphatic system individually do not account for a great many patients. Conversely, trauma-related conditions form a significant part of the caseload of an ED department, as a result of which we'll see that many of the individual clusters that have been selected are rather more detailed codes for specific soft tissue disorders at a specific site. So the level of abstraction that is chosen across the space of clinical concepts is more abstract, more general concepts are selected in areas for which there isn't a huge case mix at an ED department, and rather more specific, nearer to the leaf node concepts in areas where the ED case mix has a high volume. The potential value of such an induced classification for further case mix trends analysis will be explored towards the end of the section, looking at the graphing function of the analytics module itself, which we'll return to now. So by clicking on the Graphs section, the tool will swap to a different mode of interaction, and will begin by drawing a straight plot of the monthly footfall, the monthly case mix, so the total number of coded episodes occurring in each month of, in this case, the 39 months of data collection. And we can see from this graph that there is an overall upward trend across the 39 months, where the number of patients attending the ED department is continuing to grow. On the left-hand side are the clusters that have been defined in the editing pane of the query tool, which we can use to more narrowly focus our query. So this is a graph of all patients attending over the period of study, whereas if I say, okay, I want to only include those patients who presented with a diagnosis within the scope of the chest infection cluster, and run that, we should get back a graph showing the numbers of patients who satisfy that condition. The number is clearly a lot lower, and we can also see for chest infection in particular a very obvious seasonal trend: high volumes in the winter, lower volumes in the summer. The graph can be made larger by clicking on and dragging the upper right hand corner. It can also be copied and pasted into an external document, because it's a standard Microsoft chart object, which also means that the underlying data goes with it. The tool supports plotting of a number of different outputs. This is the total number of episodes by month. They can also be plotted by quarter or by year. We can also ask for a plot by day of the week. So for example, if we swap from the chest infection to the food poisoning category, we'll get a line graph of the number of patients attending on a Sunday, a Monday, a Tuesday, a Wednesday, a Thursday, a Friday, and a Saturday. Graphs can be plotted for patients who satisfy a single cluster or a collection of clusters. So I can multi-select in the window on the right hand side and toggle them all between the various states. At the moment they're all inclusion clauses, so now if I click the Run button, the graph I get back will be a plot of the number of patients attending on each day of the week, with a diagnosis that satisfies the definitions of either the botulism, brucellosis, enteric fever, food poisoning, infectious bloody diarrhea, or chest infection. In addition to being able to combine more than one cluster definition to frame my case mix query, it's also possible to combine cluster definitions with other metadata about the episode of care. So I'm just going to flip these back to deselect them and only select the chest infection class. But I'm also going to, if I can get the tool to cooperate, ask it to select male and female patients and perform a sub-analysis. So the first column, the O here, indicates that this wants a separate plot of the numbers of male and separately female patients. So if we run this query but ask for the monthly total graph, what we should get are 3 lines. So the black line above is the total count for patients who satisfy the definition of having a chest infection and also are either male or female. And then sub-analysis for male and female. The male line is yellow and the female line is pink in this particular case. It can be seen from the list of items at the bottom of the list on the left here, so below the set of cluster definitions, which is towards the top of the selection box, that many of the metadata items that could have been populated within the imported electronic patient record data are available as further filters on the plot that's produced. So, for example, we currently have a plot of all the patients who are either male or female and also have a chest infection. We could refine that further to say, I'm only interested in a plot of the patients who had a chest infection and also were discharged with no follow-up, and were male or female, with a sub-analysis by sex only. And we should get, again, still the 3 lines, but the total line at the top is the patients' accounts per month of those who satisfy all the criteria. They have a chest infection, they were discharged without any follow-up, and they were male or female. And then underneath the sub-analysis of those patients who were specifically male or specifically female. Another visualization of the data that's possible is the age-date graph, which I'll plot for chest infection only, so I'll need to deselect the metadata items that we previously had. So now we're only going to plot patients with a chest infection, but an age-date plot. Now, because the tool is currently set to plot a line graph, this is not so clear, so I'm going to edit the chart object to something a little clearer. We can also see we can get hold of the data that underlies any particular chart object, and we can copy and paste it to external analytical packages such as Excel should we wish to. And this functionality will be explored later when we return to the question of the induced cluster. But having got rid of the lines that join the dots, this plot's a little clearer now. The tool's just misbehaving a little bit. So what we have here is a plot. Each data point represents one consultation episode, and its position on the chart is given by time along the horizontal axis and the age of the patient when they presented along the vertical axis. And this scatter plot view shows us fairly clearly that the incidence of chest infections is quite highly concentrated. There's large numbers of them in the very young. There's a relative dearth of presentations between the ages of about 5 and 20, and then fairly smoothly right up into old age. There isn't a great deal of clustering in any particular decade of life, but we can see in the shape of the vertical stripes that are sort of present when you screw your eyes up, we can see the seasonal pattern that the clustering is in the winter months and less so in the summer months. And this kind of plot can sometimes be useful for visualizing other case mix trends that may not be so obvious from the normal time series plots. And this brings us to the final part of the case mix analytics demonstration and walkthrough, which is to return to the EPR induced cluster definition, which, as we've previously seen, will return about 97% of the entire clinical caseload. There's a small number of patients who fall outside it. And when it returns, the result looks like this. Pretty much the same shaped graph that we had right at the beginning, the original plot of monthly attendances for any reason at all. This is now the monthly attendance for those reasons within the scope of the induced cluster, which, as we know, covers around 97.5% of all patient encounters. However, this particular output isn't all that interesting. It's not very surprising that the shape of the graph is still much the same as previously, and we still don't know why or where the case mix trend increase is occurring. To use the induced classification of almost all of the EPR episodes to try and delve deeper and find out where the overall 10% cumulative increase in case mix volumes has come from, we need to change the way that we plot this graph. One of the options for query definitions specifically is a different kind of subanalysis, where we can ask it to treat each individual clause as a cluster on its own. In other words, to calculate a table and plot the resulting graph that shows us the monthly volumes of patients presenting to the emergency department for each of the individual classification concepts within the induced cluster definition. And if we run that report, we get a result that looks like this. On the face of it, not an awful lot more useful. Data series plotted one on top of the other in a way that makes it nearly impossible to determine which have increased, decreased, or stayed more or less the same in case mix volumes over the reporting period of 3 years. But the value of running this particular report is not in the graph that is produced, but in the underlying data points, which we can get at by double-clicking on the graph until the data value set is revealed above here. I can copy the contents of that and then paste them into, for example, Microsoft Excel for analysis, initially outside the tool from whence it came. In the data Excel worksheet that's produced, we have across the top the concept identifiers for the clauses that made up the original induced cluster, and for each column we have the total number of patients attending in the respective month, with a diagnosis falling within the scope of that clause for all the months of the reporting period. And we also have the grand total of patients attending for any reason at all in each of those months. We can use these data points to compute the absolute and then the relative growth rates seen in each of the clauses that we've analysed. So in this line, I'm going to compute the total number of patients who attended in the first 12 months of the 39-month reporting period for this particular clause, and in the row underneath I'll compute the number attending in the final 12 months. And then in the third row, the difference, which is the absolute growth rate. In this case, 64 more patients attended in the final 12 months by comparison with the number attending in the first 12 months of the 39-month period. I can do the same for the total of all patients attending for any reason, and this then allows me to express the absolute growth observed for one clause as a percentage or fraction of the total growth rate seen across all clauses. And then we can compute these four values for all clauses in the list. We can plot this relative growth rate for each cluster as a scatter graph. And we can immediately see from the resulting graph that there are some individual clauses, areas of SNOMED content, which are well above trend. Their individual absolute growth rate is large, and in addition, as a fraction of the total observed growth rate, they make a significant contribution. This effect is even easier to see if we sort the columns according to the metric that we plotted, the relative growth rate. We can see from this graph that only a small number of them have well above trend growth rates. Individually, they have grown quite substantially, and collectively they account for a significant proportion of the overall growth seen in the department. Because the data has been sorted in the columns from left to right, with the largest clause on the left-hand side, these clauses are in fact the ones highlighting now, all those for which the computed index is above roughly 0.05, which is on the graph, this line here. The SNOMED concept identifiers for the clauses that make up this select group are those highlighting now, but it would be useful to be able to retrieve those in a list that we can take into the Data Migration and Analytics Workbench. To do this, we'll use a little bit of Excel magic to pull back the concept identifier from the top of column C, and next to it we want the relative growth metric from the bottom of column C. And then we want to do the same for columns D, E, F and so on, but underneath rather than beside. And we can see that the concept identifiers that we want are these 13 here. So let's go ahead and paste this list into the Data Migration and Analytics Workbench. To do this, we're going to need to make a new query cluster container to hold them in. So we'll go to the editing pane and create a new cluster. Specify it's in SNOMED. And it says, do you want to paste this list into the selected cluster? Yes, we do. Don't want to refactor it. So there's the 13 high growth clusters that we've identified from the original INDUCED cluster. And I'm going to delete these auto-injected exclusion clauses because they're not required. Now it's pasted these in as just this code rather than the original code and all descendants, so I'll select the clauses and flip them all to code and all descendants. So now we've got a faithful copy of 13 clauses out of the original 120 odd from the 121 from the EPR induced cluster, and these represent that fraction of the induced classification which appeared to be demonstrating an above average growth rate. But if we run the test query function to retrieve a count of all the individual SNOMED codes within the scope of these 13 clauses, we can see how much we've managed to narrow down the search for the areas of clinical activity increase that are responsible for the overall increase observed in the department over the 3 years. And what we can see is that these 13 areas of SNOMED content between them still account for only slightly less than half of the entire clinical caseload. So we've narrowed the search a little bit, but perhaps still not by very much. Within each of these individual clauses, there may be more specific codes that are responsible for the overall growth rate. So our task now is to try and pin these down. And to do this, we'd have to analyze each cluster individually. I'll show how to do this with one of them, the pane of truncal structure. I'm going to need to create another new cluster to do this in. So in this new cluster here, I'm going to add just this clause here. The easiest way to do that is to click on the clause which copies the relevant code into the Windows paste buffer, so I can immediately add it back. It's kind of like a copy and paste, but without using a copy or a paste button. And as usual, I'll delete these exclusion clauses that are injected automatically into a blank cluster. So now we can focus only on the pane of truncal structure section of SNOMED content. If I test this abbreviated definition, then we get back a list of 163 codes from this slice through SNOMED, which collectively account for 10% of all of the codes. And we can see that the volumes of codes follow a typical zip distribution. There are a small number of codes with fairly high counts, and between them they probably account for almost all of these 37,000 episodes. So perhaps the ones to focus on most of all to see which of these codes are individually ones of increasing volume is to select those codes from the top of the list and add them to this cluster. And there's an easy way to do this. Having selected this list, it's already copied this block of text to the Windows paste buffer without having to click any further buttons, and I can immediately try to paste those rows back into this window. And when I do that, it says, okay, what you've pasted into me includes or appears to include a code column. Do you want me to add these to the highlighted cluster? So I'll say yes. I don't want to refactor the cluster definition immediately. So we can see that now we have the original pane of truncal structure and all descendants code in, but we've also got these individual clauses that we've grabbed from the list before added as individual clauses. Now, of course, these are redundant in the sense of this single clause already brought these codes in scope, but having them listed redundantly as duplicate clauses means that we can run the subanalysis section within the EPR graphing module. So if I click on the background, it'll update this list here to bring that new cluster definition into the list of things I can query on. So I'm interested in a graph plotting only patients from this high growth code cluster definition, so in other words, only those with pane of a truncal structure. And I also want it to produce the subanalysis graph for all of the clauses within the definition of the cluster. So if we run this query and wait for a little while, we'll get a graph showing us both the overall counts of patients attending with some kind of pane in a truncal structure, and then 10 or 15 additional lines beneath it, which are the individual counts for the sub-clauses within the cluster. So this pink top line is the counts for each month for patients attending with any kind of pane of truncal structure, and the underneath lines represent each of the individual codes, each of these individual clauses that we redundantly put in, but which allow us to perform this sub-analysis. As we can see, some of these have fairly low counts. There are a couple with an increasing trend over the period of time, quite a lot, the ones with low counts seem to be pretty flat. So actually, out of all the codes in that list, this one, the yellow one and the blue with blue cross lines codes, are probably responsible for almost all of the content. We can see this is the yellow one is the 2152201, return back to the editing window is abdominal pain. Not abdominal pain and all of its subtypes, but just the diagnosis abdominal pain. So I'm going to flag that one with an exclusion clause. And the second one that we're interested in is this dark blue with a blue hashed line across it, which if we scan here is this 7009 code. Scan our list, that's chest pain. So if we make both of those exclusion clauses and rerun the query, if those are predominantly responsible for all of the observed increase in the truncal structure pain category, we might expect to see a different shaped overall line. So now we can see, having removed those, the trend for that slice of SNOMED as a whole, for all other diagnoses in the truncal structure category, excluding very specifically abdominal pain and chest pain as single SNOMED codes, the trend for that slice is pretty flat. There may be a couple else buried in this set of wavy lines at the bottom, but their overall contribution is not that great. So we could see if we can find them by increasing the scale. If I ask to edit the graph, I can highlight the series at the top and delete it, which allows all the others to become much bigger. So sometimes, having done that, it's possible to see, for example, this brown set also has an increasing trend in it. Clearly, if the original cluster definition here had fewer clauses in, if we'd done it in smaller chunks, then the resulting graphs that we get here may be easier to see those individual codes with a rising trend and those with a more or less flat trend, in order to pick out the ones that we wanted. So it can be seen from that walkthrough that a slightly laborious process could be followed to go through each of the 13 this group, each of the 13 clauses that we identified, each of which corresponds to a slice of SNOMED within which there is increasing code volume. And often we'll find that that increase is actually restricted to some very specific diagnoses. But we've seen how that process is somewhat tedious and fairly repetitive. So there is in fact a much easier way to achieve the same result by asking the machine to do it all for you. And that can be done from within the Analytics tool here by clicking on the EPR INDUCED module only. Let's get rid of these. So the original INDUCED cluster, we want it to do a subanalysis, and we want to plot this specific result, the episode's period 1 to period 2 trend, and to run that test. If we do run it, then after 3 or 4 minutes we end up with what's displaying on the screen now. The graph that's produced is our old friend that we rather more tediously produced within Excel. So this is a plot of the relative increase in the growth rate of each of the 121 clauses in the INDUCED cluster, with additionally the SNOMED identifier and a cut down version of the fully specified name, so that if you copy and paste this somewhere else, it's more possible to see what each of the individual data points actually are. But also of interest is what's hiding behind the graph at the moment, which is an extended textual report. It went on, having produced these individual clusters, to look for the individual codes within them that are responsible for growth. So it's reported for itself that out of all of these, the 13 odd clusters above the level 5 line are the ones that we previously cut and pasted across from Excel back into the Data Migration Workbench. And it's placed those into an EPR. Let's click on the background here. They will be in the EPR group risers cluster. So it creates a new cluster for you and puts them in there. But underneath it, it's gone further than that and looked for the individual codes that appear to be either exhibiting quite a marked decrease, so that's the individual interesting codes within this block of clusters, or an in particular increase. And it's narrowed down the list of individual codes. So this is not slices through SNOMED, these are single code diagnoses. Narrowed down the list to just these, which are collectively responsible for 96% of the entire observed increase of all presentations for any reason. And it's placed this list of codes in the EPR code risers cluster here. So we can see them back over here. Refresh the list of codes. So we've got here is the cluster it's just made itself, and here are the slices through SNOMED clusters that have been created. So this is the slice of SNOMED or slices of SNOMED where there's a decreasing volume, and here is the slices with an increasing volume. So this cluster, which has been made by running that report, is essentially exactly the same as the one that we did rather more tediously by hand, with some slight differences in whether or not it's a self and or descendants or not. So this is the very interesting one. This is a list of just 15 specific single code diagnoses out of all 12,000 SNOMED codes that have been given during the 3 years of this department. There are just 15 codes that are selected by clinicians which appear to be responsible, or at least all the patients, all the increase in caseload is within that list. And we can test that hypothesis by now asking for a final plot of the monthly trend for the total volumes of patients attending the department for any reason at all except one of those 15 individual SNOMED diagnoses. And whereas when we plot the graph of patients coming for any reason at all, what we see is a cumulative increase of about 1,300 extra patients attending every month by the end of the 39 months by comparison with the beginning. If we just exclude those 15 very specific diagnoses, we see a more or less flat line. We can show that a bit further by asking again to edit the chart object, and for this series adding a trend line of a moving average computed over a reasonable number of months, and we can see that line is indeed pretty flat. The equivalent line for the unfiltered result, where we haven't filtered out those 15 diagnoses, showed a fairly marked upward trend. Equally, we can plot what is the trend for that very specific list of 15 clinical diagnoses. Actually, we'll make that into a subanalysis query as well before setting it going. So now we should get back the graph showing us the rise across all 15 codes that appear to be responsible for the case mix increase. And what we get back looks like this. There are a number of interesting characteristics. Firstly, we can see that the growth rate appears to have a step in it, rather than being quite as smooth as we had previously seen. Need to remove the overall summary series first before we can see the growth rate in the individual codes. Some of them experience some quite significant dips within their overall trend, others are more constant, although plateauing towards the end. So the tale that's told by each of these lines is in fact not one of consistent increase, although that's what was seen across the whole department, and further digging would be possible. For example, if we look at this list of codes, it's interesting that cerebrovascular accident was in there, and in fact in other analyses of this data set, collapse also appears. So it may be more interesting to take this particular code as inspiration to go looking and studying the incidence of presentations of cerebrovascular accident, TIA, collapse, and similar diagnoses more closely. And that concludes this walkthrough of the case mix analytics section of the UKTC Data Migration and Analytics Workbench. Thanks very much for watching.